Sir, yesterday I was trying to create the virtual environment. So with Python 3.8, sir. So I got package not found error. The following packages are not available from current channels. So
Did you use Conda or Python's create env?
Conda, sir. Conda creates -n. Pip
Name.
Python 3. Yeah, name and pip Python 3.8.
Pip.
Yeah.
No need to put pip there. Let me show you. You know, in this thing, Windows also same thing. Conda create -m, right? Maybe tflow, right? And then Anaconda Python 3.8. If you don't put Anaconda, right, it will not install all the Anaconda packages. It will just install Python 3.8 only. If you do like this, right?
Okay.
No need of pip in between.
Okay, sir.
Right? It's actually trying to install pip also, I think. By pip 3.8 maybe.
I said pip install Python 3.8.
Pip is not needed.
Okay.
Right? If you say like this, right, Anaconda packages will not be installed in the new environment. If you say Anaconda also, it will install Anaconda along with 3.8. Anaconda all packages, scikit-learn,
Okay.
everything will come.
Okay.
Any other questions?
One second, sir.
Yeah, now right after course you will have questions because you start practicing, right? Don't hesitate, ping me whenever I have time, right? We can meet or maybe I'll guide you over the phone or no. Somehow I'll try to guide you. Okay.
Yes, sir. Definitely we will get.
Yeah, we will, because you guys are actually doing good. Many people by the time we reach here, right, many people leave it. You see that, right? Initially you have seen 15 or 17 people in the class. Now I see 3, right? Maybe 2 are maybe watching videos, maybe 5, right? So that's how it becomes. That's how the subject is very intense and vast. So many people may not be able to stay here. So I would say, you know, uh, that's kind of opportunity, right? Many people cannot stay in this field because of its it's whatever the complexity, right? So market is going to be there. If we spend time and get good knowledge, market is going to be there, the demand is going to be there, and the pay is going to be high only. It is not like SAP or other packages and other stuff, right? They're easy. They are, if you look at SAP or PeopleSoft, these other technologies, right? They're easy, and market was there. And now if you see, the billing rates have come down. But for AI, it's not going to happen. The next 10 years, it's not going to happen, definitely. Okay. So you guys are understanding and have interest. So stay focused and practice and let me know, right? If you need any help. And we have work. Actually, we have work also. If you are interested, right? Once after finishing the course, let me know when you want to join. We'll assign some tasks also, research tasks also. Okay. Yeah. So word embedding. So yesterday we have seen the image embedding, right? So this is nothing but embedding an image, right? This face detection, face recognition. What we are doing, we actually are creating a network. So this is the network to which we will actually pass new record, right? This is the network to which the new number will pass and get the 128 pixel, 128 output, 128 dimensional output. Okay, and then this output we are going to use check against the database. We have many you know, we have many files, right? For all those files, how many? Oh, that's a good question. So we have 60,000 numbers, right? And 10 classes. In database, how many 128 dimensional vectors will come after doing this Siamese network? Yesterday's class, we did Siamese network, right? I have taken data, right, and then I have created this no, but metric. Sorry, the last function I need to change it to triplet last. Give me 1 second, okay? So there is triplet loss also. See this? I think this guy, I know this. He added a layer here. You know this L2 norm layer he added as the last layer they added. I don't know why last layer. Train and evaluate. Compile. Yeah. See this? Yeah. This is nice. You know we have it. You know these guys actually built it. Last time when I saw this, right, it was actually not that good. This time it is good. You know, the API changes very rapidly. API changes very rapidly, and you guys need to follow. Okay, let me put this in chat. Right, watch this. Kind of, follow this and try to build your Siamese network for what you call it as this. Uh,
Sir, like you're saying that APIs keep changing every time, right?
API
So,
gets added new things and documentation gets improved.
okay. So whenever like API changes, what about the existing ones or existing model? It will work or we need to rebuild the model again with the new API?
Yeah, that's a good question. It will show deprecated messages. It will work, but it will show deprecated messages. We need to change it.
Okay.
Yeah. So
We
if
need to
we
change it
leave,
into
if
production
we,
again.
if we leave it like that for maybe 6 months, right, it will not work. Once you see deprecated, you need to do, you need to take necessary steps. Plan it and make the changes.
Oh, okay.
Yeah. So the point here is that in the Siamese network, let me go back. Sorry, I thought like I'm going to jump into that, but if you look at this, right, we were actually passing it to sigmoid function, and L2 norm of the in our network what we did. Let me see. Yeah, so lambda layer. So this is last layer only. Okay, so lambda layer is the last layer, but this guy, this is not Siamese network. This is not Siamese network, but those guys use a triplet loss. Okay, so triplet semi, hard loss. What is that? Yeah, it's triplet semi hard loss only. Okay, so we can use triplet loss here. Let me put this and run and see what happens. Oh, TFA, TensorFlow. This is some other API add-ons. Let me try to import this. See, these guys are actually trying to, data sets also we'll see in coming class. Trying to put new APIs here. I have to install this, I think. Okay, here, let me change it. So we have the Siamese, whatever Siamese network, we have it now. Just that we need to pass images, the photos of people. Can somebody take this and do a face detection, face recognition project? This code works. Let me run this. So my question was, when after running the Siamese network, we have 60,000 images, right? Out of 60,000 images, how many records we will get in the database? How many records do we get in the database?
All 60,000, sir.
May not be.
No, sir. 1,28,000.
No.
Because
No,
each record.
suppose, let me change the statement. Now you have 1,000 employees in your office and you collected 4,000 pictures of those 1,000 employees and you did Siamese network. In database, how many records you will get? This is a simple question.
Only 1,000 employees, 1,000 records.
1,000 records. For each person, you will get 128, one vector of 128 pixels, right?
So 1 into 1,000 for
No,
each one.
1,000 only. Yeah, 1,000 only.
Yes.
For each person, that's one 128 pixel vector. So here in this problem, how many you will get? In this problem, how many you get?
60,000, sir.
No, 10 classes, right?
Okay. 128. Okay.
There 1,000 classes, we got 1,000 vectors, 128 dimensional vectors. Here we'll get the 10 vectors. That's it.
That's
Network is too simple, so we are not getting that much accuracy here. But we have, whatever we have Siamese network, whatever we have seen here is all been implemented, right? So you will get, when a new image comes in, you need to create this as a class, and this particular block as a class, and then you create an object and pass the input, and you get the 128 pixel whatever 128 dimensional vector, and you compare that vector with the database, and you say whichever that class, if it is equal to, or if it is very close to the one or maybe five record, right? You say that is the record. So you can implement that. We have almost 90% of the code is here, right? But this is diverging. See this? We have to actually make the model work, right? I did not do much there. So, and then you can actually do the whatever, right? So did you get it? Are you getting it?
Yes,
Yes.
sir.
Yes. Oh. So this is the network we need to follow. I don't know why I did this network, right? I don't know why I did it. I actually wanted to show some example of two sequential classes, merging them using model class, I think. Okay. Based on all this, right? I want to do. I was actually trying to do something on a NLP project. I was actually trying to create a ensemble neural network. Ensemble neural network. I'll try to give that exercise. Let us see if we can do it or not. So these are the projects I was actually talking about. Okay, and we have real-time projects also, but these are the ones I would expect in a class. If you can do this, right, you can do anything in real time. Okay, so let's move on to the word embeddings. I'll come back to this. If I get time, right, I'll try to implement this and show you. Okay, so word embeddings. So here in this Siamese network, what we did, we passed 128 by 128 pixel picture, 784 pixel picture, and generated 128 dimensional vector. So we actually reduced the dimensionality of the original picture that we are calling as encoded picture encoding or embedding also you can say. Okay. So encoding or embedding. Why am I saying encoding? Because we try to understand the pattern and reduce the dimensionality. It is not just a dumb dimensionality reduction. It is pattern recognized dimensionality. It's a supervised dimensionality reduction. Okay. So we can do that to text also. Why do you need to do that to text? So we have looked into the bag of words and TF-IDF. Do you remember? Do you remember the bag of words way of numerical representation and TF-IDF way of numerical representation of text?
Yes, sir. Bag of words.
Yeah. So in bag of words, what happens? What are the rows and what are the columns?
Words are the columns. And rows are the numerical representation. Zero or
Yes,
ones.
numerical representation of documents.
Documents.
Okay, documents. Rows are the documents and words are the columns. In TF-IDF? Initially, we will not remember. I know, right? Just time. This is like interview preparation, right?
Revision was
Generally asked
required,
question.
sir. Actually,
Huh?
revision was required. Actually.
Yeah. Yes, and yes. I know. I know. I'm just trying to, prepare you for the interview, right? This is like how you feel in interview. I'm trying to create a simulated environment here. Okay. So in bag of words, it is rows are the documents and columns are the words. In TF-IDF also same. Okay, rows are documents and columns are the words. In bag of words, cell values, row column cell value. What is that? What is it? Count of words, count of that particular word in that particular document, right? Each cell represents count of the word in that particular document. In TF-IDF, right? In bag of words, we will actually do that, and if stop words were not removed or there are some unnecessary words which are repeating many times, we get high score and model may get distracted. Our model, the data, noisy data gets created in bag of words when the words are not important. How do you know when the words are not important? You need to do manual analysis of data, right? You need to look into a couple of hundreds of documents and then plan your activity, whether it is TF-IDF or bag of words, which actually suits should be done, or the context based numerical representation. Word2vec is the beginning of it. Okay. So you need to look into documents. You do some frequency distribution analysis. What is frequency distribution analysis? Do you remember?
Histogram, sir.
Histogram only. How many times each word occurred in the given corpus, right? Or maybe couple of documents. Each document you take, try to see how many times, or combine multiple documents and try to see in a data set, right? It is a sample. Generally, it's a general idea. As a human being, we are trying to get general idea so that when we experiment with the tools, where things are going wrong or where things are coming right. There, you will try to find reason, right? Generally, what scientists do is they observe something, they try to create a scenario that actually satisfies their observation. That's the invention they call it as. Okay. I don't know whether how far it is a big invention, but it is already there. We are trying to find a formula or a device that actually satisfies that particular observation. Okay. So they are it's a gravity, right? Apple fell from something, some tree onto the floor, and that guy actually measured the speed and all that, and with that, they calculated the gravity, right? So that number is actually proven, because when fire a rocket, right, it is actually going out, right? So that's the kind of proof. So like that, right, you try to observe the data and find out the patterns in the data, understand the patterns at a high level, and try to build a model, and you will find reason then, right, to whether your understanding is correct or not will determine the tool which is helping you, find out right patterns. Okay, so bag of words, TF-IDF, and semantic based, word vector representation, word2vec. Okay, which one to choose? In TF-IDF, what we do, we calculate weighted term frequency, 1 plus log of term frequency. What is term frequency? In a given document, how many times a word occurred is the term frequency. Weighted term frequency is 1 plus log TF. What is IDF? Inverse document frequency. N by DF, document frequency. A word, in how many documents it occurred? Unique occurrences. Okay, a word, we have 1,000 documents. In a given document, a word may have occurred 100 times, but you take only one, count one. Whether a word occurred in a document or not, that's the DF, document frequency. 1,000 documents are there. A word occurred in all 1,000 documents, like maybe the stop word, right? Then the IDF is going to be 0, because log N by DF, right? N is 1,000, DF is also 1,000, you get 0. If a word occurred in only one document, right? N by 1, 1,000 by 1, log 1,000 is going to be 3, right? So you get document frequency is low, inverse document frequency is going to be a big number. Document frequency is high, inverse document frequency is going to be small number, right? Term frequency, weighted term frequency is going to be high when, in a given document, that term is high. When you multiply these two, right, one actually tries to penalize. The inverse document frequency is going to penalize most occurring documents in most occurring words in most documents. So stop words kind of things will get a low score because of IDF. Okay, got the analogy, right? So bag of words is brutal, brute force, so, right? So it's just counting, and it may actually create noise in the data. TF-IDF is actually trying to solve the problem of giving less score to the most frequent words, right? Most frequent words, which are like stop words or unnecessary words, right? But these two are syntactic in nature, lexical. Okay, so they may not find the semantically similar words. So, I like a movie and I prefer a movie. Like and prefer are two different words syntactically, but semantically they are kind of trying to express the same thing, right? So the word2vec, the vector representation of words, will actually try to create numerical representation that is closer for like and prefer. Got it? In semantic, the word2vec representation, the word2vec model will generate a vector for each word, where the words semantically closer to it will get the similar word. If you are trying to give one-dimensional vector, one-dimensional vector means a vector with one dimension, right? One number only. So, I like movie and I prefer movie, right? I will get one number, maybe 10. Like I got 11, and movie I got 12. Then prefer I'll give maybe 10.5, something like that. Got it? So numerically also these two are close to each other. Got it? That is word embedding. Getting it? Should I write? What is word embedding? I explained. Did you get it? No? Yes, no, no. You're all silent. I'm thinking no. Should I write and explain?
Yeah, please, sir.
Yeah. I explained the differences between TF-IDF and bag of words. Did you get that part?
Yes, sir. I got that point.
Yeah, that's a that's a good answer.
Yeah.
You don't know about others, right? So, Sasiram garu and Giri garu, you got it, right?
Yes, sir. But if possible, if you put in a
Yeah.
pictorial way, then that will be
Yeah,
easily
let me write.
remember.
That's better. So I will put all three, in written form. So there are three ways of actually there are two major ways. Syntactic. Give me 1 second. Give me 1 second. Where am I writing? Okay. So there are two ways of representing our text into numbers, right? One is syntactic, another is semantic, right? In syntactic, we have two ways. Actually, we have seen three ways, right? What do you call it is I forgot that third approach. Okay, that's okay. Right? TF-IDF, the bag of words, and TF-IDF. Third approach, we actually collapsed words and all that, right? Did you remember hashing vectorizer, right? Bag of words itself has got two, right? Normal bag of words and other is hashing. In semantic, right, there are many. Actually, word2vec is the beginning, and then glove, and then doc2vec, and there are fast text and other things are there. But the most recently transformers. Okay, these are the most popular ones. Maybe I don't know whether you actually are looking into articles on NLP. If you look at them, right, you would have found GPT, right? Bert, Roberta, right? And GPT, right? GPT is most famous now. GPT-2, GPT-3, right? These are all transformer networks that will actually give us tools to do a semantic representation of words, more appropriate semantic representation of words. There is a hugging face .com or org, I don't know, right? Hugging face, if you type in Google, right, you will get this package is providing these. These are built in PyTorch and TensorFlow both. Okay, if you are working on a TensorFlow project or Python code, you can actually, it is very simple. You can just import it and take the embeddings from this. Okay, we'll know what is this. I'll explain in like maybe today or tomorrow, right? So we are into core of AI. So this is semantic. What is the difference between syntactic and semantic? In syntactic, in bag of words, what you do? Doc 1, doc 2, doc 3, and so on. Doc M, right? Word 1, word 2, and so on, word N, right? And then right, These are all numbers, right? These are all numbers. Maybe 2, 0, 5, no, 0, 0, 2, right? Like that, right? These are all numbers. Now, how many times it occurs? In TF-IDF, right? Again, word 1, word 2, and so on. Word n, right? And here also we'll get number only. Right? For each document, we'll get number only. But the way we calculate this number is the mathematical way to eliminate or give less importance to the noisy words, right? So if there is a word is in the data set and it occurred 5 times, right, the y is going to be there anyway, right? If it occurred 5 times, the weightage for this number, this column is going to be high in all the rows, and model get distracted. Model doesn't know whether it is text or whatever, right? It actually knows numbers only. You pass big number and you have one here, it thinks that this is the most impacting feature in predicting it one, right? So while feature engineering, you should be careful of giving importance or the highest score to the features which are important. Okay, so here we are trying to reduce that. So suppose that there are 1,000 documents, right? M is equal to 1,000. If you have to calculate a TF-IDF score, you need to calculate TF score first. What is TF score? Term frequency. There is term W1, right? For W1, for each term there will be a term frequency. Okay, so for each word in a document, right? In document 1, how many times word 1 occurred is the term frequency, right? We said 2, right? And in document 1, how many times word n occurred? TF of word 1, TF of word n. Okay, right? 5, right? So we are saying that ease is a suppose that only 5 documents are there. Suppose that 5 documents are there. It's going to be easy to calculate. Okay, we said that ease is a stop word. So we need to calculate in order to calculate TF-IDF score. TF-IDF score, right? We need to calculate weighted term frequency. We call it as term frequency itself. TF-IDF, this TF is weighted term frequency is equal to log of 2. It is log of 5. Okay. And how do you calculate IDF? IDF is equal to n, log of n by DF, document frequency, right? E is occurred 5 times in the document 1, but we take is 1 only. Second also it occurred plus 1, right? 2 times it occurred. In the last also it occurred thrice, but we'll take 1 only. So totally it occurred in all the documents. So we have got 5. DF is equal to 5. Are you getting it? Document frequency, did you get it? If a word occurred in a document, then we take it as 1. We will not take the total count. Got it, right?
Yes.
So this is going to be log n by n, right? 5 by 5 is going to be 1. Log 1 is equal to 0. So when you calculate TF-IDF score, right, here you get zeros. What is TF-IDF score? Log 2 into 0 and log 5 into 0, right? So here you get 0. That means you have given 0 importance to ease. That way the data set is more appropriate when compared to bag of words. No, bag of, is TF-IDF greater than bag of words? No, that I already explained. It depends, if a document classification is dependent on how many times a word occurred, then TF-IDF, the bag of words is good. In a data set, you have more unnecessary words other than stop words, and manually cleaning them is difficult. Then you go with TF-IDF, where it will actually give less score to unimportant words and more score to important words which are occurring less. So you understood, right? TF-IDF is calculating, is actually giving less score to the words which occurred in all the documents or most of the documents. So if the data set is like that and those words are not important, how do you know those words are not important? You need to do frequency distribution analysis, then only you will know. Getting it? I'm actually talking about how to solve a problem. Getting it?
Yes, sir. But here we have actually taken the example of a stop word like is. So generally, when we do this, when we convert to
Stop word.
this into numerical representation, first we will remove the stop words and then convert this into vector representation.
Not only stop words, and in text data, right? There will be words which are not important, may occur many times also. Right? If you as an example, if I say, if we convert somebody's speech, right, into text, generally they will use some some unnecessary words in between, like I use right?
Yeah.
Right. So that kind of words will be there in all the documents, but they are not important. That's an example. You should give zero accuracy, zero score to that. If that is the case, right, then you should go with the TF-IDF. Rather, it's not going to add any value. See, ultimately, as a data scientist, we need to understand the way the things work, and then you will be able to appropriately use them. Select the approach. Got it? Right. So the third approach, the one we are going to look at it is semantic representation. Right? In semantic representation, I'll give simple example. I think initially I gave this example. Okay, initially I gave this example. Initially, when we started the NLP, right, I gave this example. Suppose that there are two documents. Doc 1, I shouldn't write many words, letters there. Doc 2, right? Doc 1 is, I like some movie, right? Right? And I prefer, movie. Right? In our, this bag of words and TF-IDF, we were taking words as columns and documents as rows, right? That all stuff. Here we'll not do that. For I, suppose that the vector size is 2, right? I said, no, what I'm saying is semantic semantic, right? So semantic are vector representation of words, vector rep of words, right? So suppose that for each word I am giving a two-dimensional vector, right? For I gave a vector 10, 11, right? And then for like, right, I gave maybe 20, 21, right? For movie, I gave a vector maybe 30, 31, something like that. Okay. To prefer, right? If you use semantic vector representation of words, a model that actually takes this text and takes each word and then tries to generate these vectors, right? Numerical representation. We are actually converting text into numbers. For what? We want to implement ML/AI, right? Deep learning or machine learning. So for prefer the model, right? Suppose that you are passing this data to word2vec model, right? The word2vec model will generate, for prefer, it will generate 11, 12. If you look at this vector and this vector, are they close to each other? Are they close to each other?
Yes, sir.
Right. So that is the benefit of semantic similarity, semantic vector representation of data. If you do bag of words, right, what happens? RTF-IDF. For like you get one column, for prefer you get another column, right? I like movie, right? The data set is going to be like this. So in prefer you will have one, right? Movie 0, right? Here I will have 1, 1, 0. So they both look different, and the data got diluted, right? The data got diluted. Maybe you have y value 1 here, 1 here. In one place this column is affecting, in one place other place this column is affecting. So when the equation is generated, right, It doesn't know whether to give more importance to this or this. Model will work here and there. But if you represent data in vector format, which are close to each other, and you try to use these numbers to build model, how to use it, I'll talk about in a moment, right? Then model will be able to perform better. Okay, that's the analogy of word vector representation. Semantic similarity, right? This is similar to this because the words are okay. Sorry, I think I should have. Sorry. I give me 1 second. Not this is like and prefer are the similar ones, right? 2022, maybe 22. I'll do. Right? This and this are the like and prefer, right? Like and prefer are the similar words, right? For these two words, we got vectors close to each other. If you use this numerical representation, right, model will understand, right? The classification model will understand better. Got it? I am trying to explain what are word vectors, right? What is the use of that word vectors? Got it?
Yes.
Move on. Okay. So now, right, the next problem. I said that bag of words and TF-IDF will work, but they actually take syntactic similarity. The word2vec, glove, doc2vec, and transformer networks will actually represent each word as a vector, and they'll have closest vectors for the similar words, right? Semantic similarity will come, right? So that I explained. But now, can we use this vector represented data to build a machine learning model? That's a question, right? So what happened here in our TF-IDF for bag of words, we took doc1, doc2 as row, and we created a two-dimensional array, right? We passed it to machine learning model and we trained it. But if you have to create doc1, if you have to represent doc1 numerically now, can you tell me how can I represent it? 10, 11, 20, 21, or maybe I'll put it this way. 10, 11, first vector, 20, 21, right? And then 30, 31. That's document 1. This is document 2. 10, 11, 20, 22, 30, 31. See the difference, you see, in bag of words and TF-IDF, total data set became a two-dimensional matrix. But here, each document is becoming a two-dimensional matrix. Can we do machine learning model with this? This vector representation data, represented data. Can we? Can we use this vector represented data, this document 1 and document 2, to build a machine learning model?
Yeah, if we establish a relation between these numbers versus output, yes, we can.
No. The first thing is you need to format, you need to frame the data set, right?
Yeah, that is what, sir. So against these numbers, if we assume that these are x parameters or something like that.
How will we do it as x parameters?
See, for example, okay, the D1 matrix what you formed inside that with the numbers, if you consider as, let's say, the matrix itself is an X, and then D1 is the Y. Another matrix of D2, that is the X.
So you get some kind of this kind of a matrix, right?
Yeah. That's what I'm just visualizing.
Yeah, you are thinking actually, right? So one way, if you want to build a machine learning model, machine learning model always expects a 2-dimensional array, right? This is actually 3-dimensional here, right? The y you leave it aside. Y anyway you can pass separately, right? So X became a 3-dimensional matrix. You cannot pass it directly to machine learning. One way is that you can flatten it, right?
Okay.
Flatten this array, right? Each of these, these arrays, you can flatten them and create a 2-dimensional array, pass one as a, the y value and pass it to the machine learning. The problem is that in real time are the word vectors. Generally we do 150 dimensional or 300 dimensional, vector for each word. Then, right, what happens? In a document you may have 600 words and each word is 150 dimensional. You will get a 600 by 150 dimensional matrix. Actually we will not represent like this. No, you take each word vector as a row, 10 comma 21. I think I have represented it wrong. So after doing the word vector representation, right, doc 1 is going to be 10, 11, 20, 20, 21, 30, 31, right? And then doc 2 is going to be 10, 11, 20, 22, 30, 31. It's going to be like that. So here, we have only 2 documents and each document has got 3 words only, right? So we have got, 2, 3 by 2 because the word vector dimensionality is 2 and we have 3 words only, word count is 3, right? If you have, word vector size 150, okay, and word count in a document 600, what happens? Then it's going to be 600 by 150, right? The first words vector, second words vector, third words vector, this is 150 only, 150 columns. So each document becomes a 2-dimensional matrix, a big matrix, right? 600 by 150 means how much? If you flatten it, what happens? 600. Right? You get 90,000 features. Okay. For each row, you get 90,000 features.
So 1 second, sir. So what is this 150 number, sir?
So, till this part, the upper part is clear?
Yeah.
So what is this 2?
So, two documents?
No. Right? This is the vector for I. This is the vector for like. This is the vector for movie.
Okay.
Right? This is the vector for I again. This is the vector for prefer. Right? Semantic similar, vector. Right? And then movie. Right? So if this vector size, you can actually decide this vector size. You can actually take 2 or 20 or 150 or 300. If I decided to have for each word a 150 dimensional vector, and in a document if you have 600 words, here in a document we have 3 words, here also 3 words, so we got 3 rows. Okay, in a document if you have 600 words, you will get 600 rows and 150 columns, because the word vector size you decided to have it as 150.
Yes. Yes.
So now if you want to flatten this and try to do machine learning model, it's going to give you a too big of a data set, right? Too huge data set, right? 90,000 columns it will, we will understand more. You will get even more number of whatever, right? So 90,000 columns you get. If you want to build a model, machine learning model with that big a data set, curse of dimensionality will come, right? You again need to apply dimensionality reduction techniques, which are blind, right? So if you want to apply deep learning model, DNN, if you apply DNN model, what happens on a 90,000 column data set? 90,000 column data set, and the first layer has got 100 nodes, maybe 10 nodes, second layer 10 nodes, like that. What happens between the input layer and the first layer? How many weights you will get?
90,000 into the number of nodes, 10.
Yeah, 10. 90,000 into 10. If you add bias term, 90,001 into 10. Bias node is not there, then 90,000 into 10. That's a huge matrix, right? Machine learning, no way you can work, because if you flatten it, it's going to be too big data set. And machine learning algorithms, most of them cannot handle huge volumes of data, right? So that is ruled out. Deep learning also, to some extent, if you have huge RAM, you can actually do it. The other solution is that you need to combine CNN and DNN. Once after converting your words into vectors, only way you can work with is CNN and DNN. If somebody doesn't know CNN and DNN, and they said they worked with the machine, they worked with the text data and the computer vision, you can just end that call there itself. When you are taking interview, right? If somebody says they worked with NLP and computer vision, and they don't know CNN and DNN, you can just end the call. This is the one question you can ask. I converted text into word embeddings. Now I wanted to build a model. How will you do it? If they say machine learning algorithm, random forest, this, that, right? Gone. Okay? So that's how industry is right now. That's where the industry is. Most of the people doesn't know how to convert a word into vector. That's first thing. Even if they know how to convert a word into vector, they don't know how to build a model using that. Whether deep learning works or machine learning works, they don't know. Maybe you can test, some of your friends who are actually working in the industry, who are not from our institution. Okay? So you got clarity, right? Right? We actually understood why are we converting words into vectors to get semantic similarity like this, right? And then once after converting words into vectors, if you need to build a classification model or any model, you need to use CNN and DNN based combined, neural network. We will look into one-dimensional convolution, right? Once after finishing this word2vec, right? So let us jump in and understand what is word2vec and how exactly the vector representation is being done, right? So I am saying that the model will generate, the word2vec model will generate a vector for similar words, right? Vectors for similar words that are semantically similar will get same kind of vector. How? And how that word2vec is working to generate this, that we will know now. Okay? So internal mechanism of word2vec, how is it actually working to generate closest vectors to semantically similar words. Okay, that we are looking into now. So word embedding is a vector representation of words. We have seen that. Word2vec is a more sophisticated word embedding technique. This technique is based on the idea that words that occur in same context tend to have similar meaning. What is same context? Where is that sentence? So I like movie and I prefer movie. These are two documents, right? And like occurred between I and movie. Prefer also occurred between I and movie. Context, I and movie are the context. Okay. In similar context, whatever words occurring are all similar. That's the point I am trying to make. Same context tend to have similar meaning. Okay, that is the most of the places situation, right? It is not always true, maybe, may not be, but most of the situations, same context tend to have similar meaning. So we should give the vector representation of those words which are occurring in same context, the similar vectors. Okay, the words which are occurring in same context should have similar vectors. So like this, the way we did here, right? So 2021 and 2022, I manually gave it, but the word2vec model will actually generate it. You pass some text, it will automatically generate those vectors in such a way that they are going to be close. The same context words are going to be close. Okay. The word2vec model, it is called as embedding, right? Encoding or embedding. Okay. So dimensionality reduction, they can simply call it a supervised dimensionality reduction. They said embedding, and initially I used to think a lot about this embedding. When I don't know, I used to imagine many things. But once after looking at it, right, it is very simple. There is nothing big. Okay. Word2vec model will train on generated supervised data set. This is the most important point. So if you have uh, maybe 1 million documents, each document of size maybe 100 words, right? You pass those 1 million documents, you pass that corpus of 1 million documents to word2vec, it automatically generates the vectors for the words by looking at a same context word. So it need to generate a data set from the input data only, no y variable. You're understanding, right? No y variable. We are taking all those 1 million documents, and then the word2vec model will generate a supervised data set using it. How will it generate? I'll explain in a moment, right? It will generate a supervised data set and then train the model on it, train word2vec model on it, and it understands the patterns. Now you pass a word, it will actually give you the vector, a 150 dimensional vector or 300 dimensional vector. Okay. So TF-IDF and bow vector representation fail to maintain importance of context or semantic similarity. Okay. The word2vec generated by the word vectors generated by word2vec carry the context and reduce the dimensionality of the vector. Context and reduce the dimensionality of the vector. So when I say dimensionality of the vector, right, you will understand. Reduce the dimensionality of the vector is actually dependent on how the word2vec is actually initially taking each word as a vector and then trying to convert. Okay. So outcome of word2vec model are the weight matrices, right? Are the weight matrices. Okay. So we'll understand all these points and come back to this. Today I'll go through it briefly, for next 20 minutes. Tomorrow I'll, explain everything in detail. Okay. It needs a little thought process involved. So you need to think about it, right? So tomorrow you'll be able to think along. So word2vec has got two approaches, skipgram and continuous bag of words. So let us look at skipgram approach, right? What is skipgram? It takes the context word, and tries to generate surrounding words. Okay, what is context word? What is surrounding words? In this, right? I and movie are the like is the context word, and I and movie are the surrounding words. It takes I as input and like as input and tries to generate I and movie as output. Okay, something went wrong. My laptop is acting weird. Okay, so like is the context word, prefer is the context word, I and movie are the surrounding words. So the word2vec network takes like and tries to generate I and movie. Okay, so I'll show you how will it actually do that, and all that I'll show you. That is the skipgram model. Okay, so let us see how exactly the data set is being prepared. See here, I said word2vec model will be trained on generated supervised data set. I think I should take out A here. Now will be trained on a generated supervised data set. What is that generated supervised data set? We'll see. Suppose that this is a document. I want to take deep learning classes from Datajango. Okay, that's the document. Okay, in this document, if you take this document, word2vec skipgram model will try to generate a data set like this. It takes I, the context word. What are the surrounding words? Want and to. It takes want and what are the surrounding words? I and to and take. I is the surrounding word, to and take. It takes to and generates I want, take, take deep. Take is the surrounding, context word. Want to, deep learning. So it is actually it is taking only the surrounding two words, right? That is called as window size. If I specify window size 1, it will actually consider only the before word and after word. If I say 2, before 2, after 2, it will consider. Right? If I say 3, before 3, after 3, it will consider. So like this, it will actually form a data set. From our whole data, I have taken one example here of one document. If you have 1,000 documents, 1 million documents, it will form a big data set like this. Something happened. Big data set like this. Right? Now it generated a data set. Now it need to build a network, right? Build a network. What is that network? What I said in continuous the skipgram model, it takes the context word and tries to generate the surrounding words. So that means it's a neural network. It's a shallow neural network. You pass one word, you try to get the surrounding words. Surrounding words are what? These surrounding words. So when I say I pass one word and getting surrounding words, I should be passing some numbers and should be generating some numbers, right? Do you agree?
Yes, sir.
Do you understand how the dataset is being formed with window size?
Yes, sir.
Yes, sir. This is fine.
This is good, right? So now you need to build a neural network that actually takes the context word and generates the surrounding word. When I say takes the context word and generates surrounding word, it's a deep neural network. It needs numbers. So you need to actually take initial numbers, initial numerical representation of these words, right? So that initial numerical representation is done like this. It's a one-hot representation of your total data. Okay. So I have taken only one document here and trying to show. Suppose that there are 1,000 tokens in your corpus. 1,000 tokens means 1,000 different words in your data set. Then you will take a 1,000 dimensional vector representation for each word. For I, you will have 1,000 dimensional vector with 1 in the first place and rest all are 0. Okay, one hot representation of your corpus, your tokens you are going to do. For want, first 0 because we already gave 1 here, so second 1 and rest are all 0. Third word, third one, rest are all 0. Fourth one, fourth word, rest are all 0. Like that you represent. Now you pass this vector as input and try to generate the surrounding words. Pass this vector, try to generate the surrounding words. Pass this vector, try to generate surrounding words. So far what we did, we understood how word2vec is forming the data set and how the word2vec initial representation of the words is being, what is the initial, vector representation of the words. 2 points we understood. Are we good so far? Are we good so far? Why this representation I'll explain in a moment. This is a very intelligent, I like this approach very much. This is a very, very intelligent, way of representing data. I'll show you in a moment. So far, are you good?
Sir, here I is a column vector or a row vector?
No, it is not. It's whenever you say vector, column vector only. Vector means column. That's it. This is not a
Okay.
table, basically. This is just individual vectors. They are.
Okay. So it's a column vector which has
Only one number 1 and rest are all zeros. First number 1, rest are all zeros.
rest of zeros means the next zero is representing one want. Is that right?
No, it is not about Yeah, what you said, what want is what? I didn't get you. I
So
didn't
in the
listen.
first, yeah, sorry. So the first place it is for I it is 1.
Ah,
And what are all the beneath zeros represent?
we'll see that in a moment. It is just initial representation. It is like, if you are understanding gradient descent, I said, weights are randomly initialized. Is there a meaning there? No, right? While learning, things will change. What will change, I'll explain in a moment. Okay.
But it looks like there is some pattern, right? For want, we are giving the first number in the vector as 0 and the second number as 1.
Yes, Andy.
Because want is occurring in the second place in the document.
Yeah, not in the document, all tokens. You take all tokens. This is just one example, right? So I took simple, sentence there. Don't take this literally, right? In a huge data set, there will be 1 million word tokens or 1,000, 10,000 tokens. In those tokens, it will choose the second word, third word, like that. It randomly choose it may, okay, and then assign the uh, unique vectors like this, right? Unique vectors. This is unique vector representation, right?
Yeah.
Unique vectors. Now, right, let us look into the model, the word2vec model also. Then you will understand. Your questions will all vanish. So this is the network now. What I said, I pass class and generate the surrounding words, right? Let us look at the data set. Class has got deep learning from Datajango, right? So deep learning from Datajango. See the deep's vector representation. 1, 2, 3, 1, 2, 3, 4, 5. In fifth place there is 1, right? Right. Learning sixth place 1. Class seventh place 1. From, right, 1, right, like that. So if you look at this network, it is taking class and trying to generate deep learning from. So the network will try to generate. It takes 1 here in the seventh place, 1, 2, 3, 4, seventh place, and tries to generate 4 vectors, which have got, in fifth place 1, sixth place 1, eighth place 1, and ninth place 1. That's the network, input and output. Are we good? How will it generate? I'll talk about it in a moment. Are we good? So far, are we good?
No, sir.
No?
Input and output seems to be same, so I don't know what is the difference.
Input and output?
No, for class, whatever the representation you showed on the left hand side and here on the right hand side, it's same, right? So
No, not same. Observe it carefully. We are passing 1 vector here and generating 4 vectors here.
for the surrounding words, sir.
See that, I even, is it visible? Is it visible? Should I increase the font?
No, it's visible, but on the input side, left hand side also, there's so many are there, right? So we don't know what is for what. That's what is confusing, at least for me.
No, left hand side, they are all words, one after the other. I'll talk about that. Just focus on whatever I am trying to explain. So you pass class.
Yeah.
You are generating on the right hand, extreme right. You have 4 vectors being generated, surrounding words, right?
Yeah, that's clear.
That part is clear, right? So now you passed class here, right?
Sir, one question, sir. Here, like we need to use only 4 surrounding words, 2 right and 2 left.
That depends on window size, and the model word2vec has got a parameter called as window size. If you specify 2, it will take 4 surrounding, left to right.
Means
You say 10, right?
hypertuning, sir?
There is, I'll show you. It's all code, right? I'll show you. Word2vec has, word2vec model has got that parameter.
Okay.
When I write code, right, I'll show you how to do that. We have examples for that. Okay. For now, think that it is taking only 2 left, 2 right. Okay. Good.
Yes, sir.
Okay. So now, right, this is a neural network, right? You know this is a neural network. This is input, right? X1, X2, X3, and so on. Xn, right? X1000, 10,000. Sorry. 10,000 distinct words, so the vector size is going to be 10,000, right? I have taken 150 nodes, okay? In the hidden layer, it's a shallow neural network. I have taken 150 nodes. And the output layer, I have got a softmax regression classifier, multi-class classification for each of these, So this softmax has got 10,000, classes, 10,000 classes, 10,000 classes, 10,000 classes. Okay, that's the network. Now, in the first iteration, if you are doing normal neural network, forget about this class, the output and all that. If you are doing normal neural network, what are the values in this first iteration of this this whole web? If it is a neural network, what are the values in this web?
Weights.
Weights. Is that random or some learned weights?
Initially, there will be some random.
Random, right? Yeah. Wait there. They're all random, right? Now, you need to when you have random values here and you are passing this class vector, right? Class, this is a record, this is record. You are passing this class vector. You are trying to calculate the activation function here, right? Right? Maybe ReLU. Take it as ReLU. Okay. So if you have to calculate ReLU, what will happen here? These are all random weights and multiplying x1, x2, x3 and so on xn. Agreed? Give me 1 second. So here, right? If this is ReLU, right? If this is ReLU, what happens to that ReLU? Think once. 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0 you are passing, and there are how many weights here? 10,000 weights, right?
Yes.
Out of those 10,000 weights, which one will come? Which one will survive and come here?
Only class.
Only that one. That one, whatever the weight that is multiplying one will survive. Rest all will vanish. Right?
Yes.
Right? In here also, in the second node also, there is a different weights, different 10,000 weights here. That one weight which is coming from this one will survive. Rest all will vanish. In the third one also, there is a distinct weights here. And only that weight which is coming from one will survive. Like that 150 numbers which are coming from this one, right? The weights associated with this one only get populated here. If it is ReLU. Got it? That point is clear, right?
Yes, yes.
Okay. Now we are passing these 150 weights to softmax, right? These softmax, and trying to generate the surrounding words. Okay, that one iteration is over, right? That class is went in and tried to generate surrounding words. Okay. Now want came. When want came, only the weights which are associated with one, right? This one, right? These weights, this set of weights which are associated with one, they get adjusted. First iteration, when class went in, they're all random weights, right? You come back, take want, the weights get adjusted. Which weight get adjusted? Which set of weights get adjusted? When you pass class and come back, in the back propagation, which weights get adjusted? For class, you did the random weight initialization and came back. In back propagation, which weights get adjusted?
Only the weight which is associated to one.
Yes. The only weights which are associated with this one will get adjusted. Okay. Now you are passing want, right? The one, now the weights which are associated with one will go in, right? And go in, and then try to generate its surrounding words, want's surrounding words. What are want's surrounding words? I to take, the one which is not there, it will actually take 0 vector. Okay. There are only 3 vectors, so fourth vector it will take zeros. Okay. So I want it take, right? So it is going to go and come back propagation. Only these weights get adjusted, right? And the learner, again, it will go forward, right? Those weights which are randomly initialized in the initial step for first iteration of all 10,000 words, they get adjusted one time, right? In the next iteration, again class comes in. This class vector will not change. It will stay like that only. Again, those weights will get adjusted. Again, those weights will get adjusted. Again, those weights will get adjusted. Only the word which is going in and trying to generate surrounding words, only those weights get adjusted. Got it? That point clear? Clear? No?
Yeah, yes, sir, but how these 150 weights, let's say if you take the input record as class record, class vector, for that, there are 150 layers, and because of it, there are 150 weights. When you
No,
pass this
nodes 150, 10,000 weights there.
Yeah,
Nodes
10,000
150.
weights. Yeah, 10,000 weights, but these 150 values will be passed to the softmax, right? Because of 150 layers. So how this softmax is actually finding out those?
That is, that is softmax responsibility. Don't think about that now, because machine learning is for that only, right? It will actually look at the cost function. Cost function is the basis. Error is not good, it will adjust the weights. Error is not good, it will adjust the weight. It is mathematical equation. It's a function which is getting adjusted on its own by looking at the cost function, correcting, self-correcting by looking at the cost function. Got it? Got it? No? Don't focus on it now. Let us finish this understanding, then we'll go there. Okay?
Yes, sure.
So these 150 nodes, right? After, suppose that, after 10 iterations or maybe 100 iterations, class, when you pass class, right, you are getting surrounding words, exactly surrounding words, one hot vectors. Suppose that. Then you can take these hidden whatever node values as the representation for class, because, when you pass class, you are getting 150 numbers. You pass these 150 numbers, you are getting the surrounding word. That means this vector can represent this class, this word. This vector can represent this word. That is the word embedding. This is the word embedding. In word embedding, the hidden layers values, the hidden layers outcome is taken as the vector representation. Okay, that's the point. And they are going to be weights only. They are adjusted weights, because the word has got 1 as the value in the x, right? These are weights only, right? Only the weights which are understood, right? The adjusted weights which understood the pattern, will take that as the representation for class. Want for representation, learn representation. So for each word, there is going to be a different, once after learning this whole thing, right, you pass words and get the vectors, 150 dimensional vectors. So now coming back to the question asked by Shashiram, right? It is the same thing happening, in a neural network. Whatever is happening, the same thing is happening here also. Whether you pass 10 numbers or 100 numbers, you generate 10,000 numbers, you can generate it. The neural network will generate it, because it is always looking at the cost function. Cost function tells it whether it is correct or not. Accordingly, the weights get adjusted and it will actually generate. So if you take softmax 10,000 classes, there is an equation for that, right? That equation, those thetas will get adjusted, right? For 10,000 classes, you will have, for each class, there will be 10 theta sets, right? So 150 theta sets. 150 theta sets for 10,000 classes. Those theta sets get adjusted. That's where you get these values. Got it? No?
Yes, sir. So what will be the y variable? Are we sending y variable?
That's what, right? The word2vec model will actually form the data set like this. This is X and this is Y. Context words are X, surrounding words are Y.
Y, yeah.
right? It's a semi-supervised learning, you call it as, right? So you take you form the data set, and what are we trying to understand? The context, right? The context and the surrounding words, right? In which context the word occurred, the surrounding words actually decide. Right? The basic imagination, the basic assumption is that when a word is occurring, when distinct words are occurring in different context, same context, those distinct words have got same meaning. So that essence is extracted by this particular neural network. That is word2vec neural network. Okay. So I'll stop here the class, and tomorrow we'll start with from the beginning, and then we'll explain again.
Sir, once